Good morning. This is Murali, Assistant Professor of Department of Mechanical Engineering, St. Joseph's Institute of Technology, OMR, Chennai. In today's session, I'm just going to explain you about how the experimental investigation on EDM parameters on Inconel 65 using conventional tool versus additive manufacturing tool, that is by using a special technique called metal fused filament fabrication technique. So normally in this video session, I would like to explain you about what is the basic fundamental things between the conventional machining process versus the traditional machining process. In today's technology, the unconventional machining process is the booming technology where we are going to machine the various parts of technologies like ultrasonic machining, wire cut EDM, so electrical discharge machining and the water jet machining. In this phenomenon factor, I will be explaining you the most important phenomenon factor, how the EDM parameters works on the superalloys material like Inconel, Monel 400, 625 and special materials like Hastelloy CSU 76. So this is in today's presentation. The overview of the presentation is introduction, advantage of the EDM parameters, needs of unconventional machining process, advantage of additive manufacturing tool, selection of workpiece material, objective, the process parameters of evaluating factor, how we are going to evaluate the input parameters on the output parameters like MRR, surface roughness and overcut, and the literature review and what is the latest literature gap where we are going to identify in the latest scenarios with the existing technologies, and the methodologies. So methodology in how we are going to prepare the tool in a special technique called the filament fabrication technique by using a copper filament in the 3D printers. So next is the preparation of the additive manufacturing tool by using a special technique called triple M methods. So what is triple M method? So triple M method is metal fused filament fabrication technique where we are going to use a copper as a filament, where you are going to extrude in the nozzle by giving a special heat addition process through the nozzle. It will fuse the filament and it will print layer by layer. So the normal size of the filament diameter is 1.75 to 2.5 mm diameter it's going to range. And finally we are going to optimize the parameters and discuss about the discussions with the references. So now I'm just going to tell you the basic parameters, how the literature, how the working principle of EDM is going to work. Normally EDM is nothing but a metal removal process by using an unlimited spark between the workpiece and tool. So where we are going to have a atomization in terms of evaporation of melting the workpiece over the tool chip interference contact. In EDM, the main thing is the potential difference is applied between the tool and workpiece. So most important factor is anode and cathode, where the tool and workpiece will be connected in between the terminals. So generally we are going to use the deionized water as a dielectric medium, such as kerosene, distilled water or any specialized mineral oils. So depending upon the potential differences, that we call it as voltage gap, that has been given between the electrode and the workpiece in between, which is established depending upon the machine surfaces. So generally the tool is connected to the negative terminal, that is cathode, and the workpiece is being connected to the anode. So generally the workpiece and tool is being connected where the spark discharge between the tool and the workpiece will take place by using of dielectric medium. So it acts as a flushing pressure to remove the debris from the workpiece. So next is what is unconventional edges out, why the EDM process play a phenomenon factor. That is, the EDM is a non-traditional machining process where the spark erode the material. It operates the controlled erosion with the ideal of hard material. So normally electrical discharge machining, wire cut EDM, we uses to machine a very hard material like superalloys, Inconel alloys and nickel based alloys. So the spark is an innovation how it works on EDM. So workpiece, that is a conductive material, and electrode, which is a very sharp tool of any cross-sectional diameter like a circular cross-sectional, hexagonal cross-sectional, a triangular cross-sectional, depends upon the specification how we are going to impact on the workpiece. So first is we are going to use a submerged dielectric medium, that is distilled water like hydrocarbon with a applying of appropriate electrical spark. Next is the spark ionization of dielectric medium by hopping a properized channel with the intense spark melting. The amount of material is being removed, that we call it as MRR, material removal rate. So volume of material removed per unit seconds. So now is dielectric flushes out the debris particle and cool the surfaces, which increases the very good interference contacts between the tool and the workpiece. So next is we are going to tell you what is the advantage, and what I'll be explaining how it's going to work on the basic layout diagram. One is the machining. The EDM machining process is primarily used to machine a very hard material, that is EDM, with the material like superconductive materials, like the intensive capacities and steel, without a needs of special heat treatment to soften and reharden them. So in this diagram, it is clearly explaining that how the electrical discharge between the workpiece is being delivered between the tool and the workpiece. So when the tool is being fit into the vertical direction, so now the gap between the workpiece, with the help of dielectric medium, this part is a very small debris will be flushed out when the dielectric medium is being concentrated with the high pressurized fluid. So normally this method can be used to in very super metals and super alloys like titanium, Astalloy, Inconel, 625 and other hardened workpiece material. So next is, the next slide we are going to know what is the needs of unconventional machining process. In day-to-day life, in the previous methodologies, we will be using the traditional method. So unconventional needs is you will be having no physical direct contact between the tool and the workpiece. So first thing is the electrical discharge machining is an unconventional machining process that remove the workpiece from the material. So like the parameters like machining of hard material, complex shapes and fine structures, low material wastages, material compactability. The most important thing is the complex shapes and the fine geometry. So normally in machining of any complex geometry structures like circular pattern or tool path pattern, geometrical hexagonal pattern, this complex shapes and fine features, it can create the sharp corners and deep cavities and small holes that can be easily machined by using this technique. So this is the basic needs why you are going to use the unconventional machining process. So now I will be discussing on advantage. So there are various advantages when compared with traditional machining process. So the unconventional machining process play a phenomenal vital role in the following applications and advantage. First is need to have a very good conductivity. So normally while choosing the workpiece material, before choosing the workpiece material, we have to identify first it is a very good thermal conductivity between the tool and the workpiece. So high layer of packaging density, improving the packaging density and electrical performance on additive manufacturing tool. Next is structure stability, lightweight and design, easy customization, faster prototyping. So in this technology, I am going to use a special technique called additive manufacturing on metal fused filament fabrication. So normally the readily available is electrode is conventional tool. So in this case, in various latest research technologies, I am going to tell you about what is the latest tool available, that is printing on the 3D printers. So in the 3D printers, we can easily have a very fast customization and faster prototype and enhance the product development. So first is easy customization. So what is easy customization? In additive manufacturing, we can easily print any type of layering tools, that is in any direction, x-axis, y-axis and z-axis, based upon the specification, and the customization can be easily done on the workpiece in order to reduce the machining time with a very good accuracy and surface finish. Now I will be talking about the major advantage of the additive manufacturing tool over the machining process like EDM. So first is I'm going to explain you on the two important comparative reasons. One is on additive tool, other one is conventional tool. First is flexibility and complexity. So whereas in the normal conventional copper tool, a very limited complexity when compared to AM tool, whereas AM tool has a very high complex geometries with any internal features during the structural operations. So next is leading time with the customization. So whereas when comparing with the traditional and the conventional tool, the rapid prototyping play a phenomenal vital role when compared with conventional tool. For example, this lead time customization lead to play a vital role in the 3D printing technologies where we cannot do it in the normal conventional tool. Next is material selection. So normally we going to print the wide range of materials including the metals and ceramics in terms of filaments, powders, copper bindings and the super bed, powder bed filament fabrication techniques. So we are now general conventional, we will be using a very rigid solid like copper on the graphite or the copper materials or any other superconducting material. Next is surface finish and precision. When compared to conventional tool versus AM tool, this AM tool phenomenally gives a very good super finish and so material surface roughness when compared with the normal traditional tool. Next is cost wise, the additional additive manufacturing tool is very expensive when compared with conventional copper tool, since because the processing, layering, washing technologies and the time requirement and the filament used with the nozzle 3D printing is very costly when compared with the conventional tool. This is the basic advantage where we are going to state how the conventional tool versus AM tool play a vital role. In this comparison, we strongly convey that AM tool, that is additive manufacturing tool, is going to play a phenomenal role over the conventional tool. Yes, so in this methods, I am just going to use superalloys. So normally in electrical conductive material, a very hardened workpiece material like superalloys, hardened materials, Asst alloy, C276, titanium carbide, boride, beryllium copper, any hardened material can be used. So in this phenomenon factor, I am using a special superalloy called inconel 625. So normally why the inconel alloy is being called as superalloys? So inconel alloy is classified as a superalloys. Basically, it exhibits a very good mechanical properties, strength, oxidation resistance, corrosion resistance, even at a very high elevated temperatures up to 892 to 1800 degree Fahrenheit. So it is a composition of highly based nickel based alloy with chromium, molybdenum, niobium, all together it enhances the stability and durability with the extreme environmental structure. This makes vital applications like aerospace, marine and chemical processing, nuclear applications. So this alloy play a vital role in various applications with the key reasons to be considering it as a superalloys. Yes. Next is why the copper tool is used on EDM. So normally there are various tools available on the EDM machining process. Normally we use graphite. Instead of graphite, in up to date latest technologies, they are using copper. Why? Because the copper is a very high electrical conductivity with a very good spark generation, which is easily essential for material removal rate, that is MRR. It has a very good excellent thermal conductivity, a good machinability and surface finish, minimal tool wear and compatibility with the inconel 625. The most important thing is the thermal conductivity and the minimum tool wear. So when compared with the normal traditional tool and the normal AM additive manufacturing tool, the tool wear is going to phenomenally differs while during the machining process. So compatibility with inconel 625 is the inconel is very hard to machine. So whichever material is very hard to machine, we can directly go for EDM process or wire EDM or ultrasonic machining process. Among this, the most availability in the industries is EDM, that is electrical discharge machining. In that electrical discharge machining, we have two types. One is fully submerged, one is semi submerged. So why we are going to select the inconel for 625? So these are the important factors while choosing the inconel 625. Most is electrical conductivity, high thermal stability, resistance of thermal cracking, work hardening resistance, machining dimensional accuracy, and uniform material removal rate. Among these following factors, the reason for selecting the most important factor is the resistance of thermal cracking. It can withstand a very high thermal stability during hot and high elevated operating temperature, that is from 1800 Fahrenheit Celsius. So normally the material removal rate will be very uniform, that is like in the homogeneous microstructures. So this homogeneous microstructures I will be discussing on the conclusion with the latest SEM technologies and microstructures comparative study. This gives the homogeneous microstructures and gives the exact result between the conventional versus the additive manufacturing. So next is objective. So normally many researchers have categorized the 3D printers versus conventional. So in this session, I could very be precise on this. The following objectives. The first objective is to analyze the effective additive manufacturing on the EDM machining parameters in comparison with the conventional tool, to analyze the effect of post-processing and pre-processing of additive manufacturing tool, to study the influence of microstructure, that is the machinability of superalloys, and also to identify the significant machining parameters, that is the performance and their percentage contribution, and the last one is to identify the machining surfaces, that is material removal rate, and SEM analysis by using the microstructure and the SEM terminologies to compare the study. Yes. So now I'm just going to tell you about how the process parameter is being evaluated on the unconventional machining process, whether wire cut or the EDM process. These are all the basic control parameters. So control parameters like the pulse on time, pulse off time, voltage, and spark, that is spark gap. So this control parameter is going to have a processing performance measures like material removal rate, surface roughness, overcut, and tool wear. So where the tool can be of conventional tool, AM tool. So where in this session I will be using only this conventional and additive manufacturing tool, where we can implement it on the special machinery called, that is model EDM 5530, that is NVNC technologies, that is being machined, right? So now EDM process parameters. So what is electrical discharge gap? As I said in the previous slide, so tool and the workpiece, you have to maintain a proper gap voltage. So normally this voltage is applied between the tool that is been acting as an electrode and the workpiece which is acted as an anode. So determining the spark distance. So this spark distance will create a significant effect, that is higher voltage means the larger spark will have a better surface finish but lower accuracy. So lower voltage means the smaller gap, it means the higher accuracy with a very high short of circuits. So next parameter is, I am just going to describe on the peak current, otherwise we call it as high peak current. So maximum current. So what is maximum current? So maximum current during the spark discharge, the electrical spark discharge between the tool and the workpiece, which is being directly controlled by the spark energy, where it have a significant effect such as high current. So high current will have a very high MRR. What is MRR? Material removal rate, a rough surface finish, increased tool wear, lower cut, that is lower material removal rate, and fine surface finish, and very less tool wear. So next parameter is pulse on time. So what is pulse on time? The duration for which the current flows during the every spark. So that have a very two important effects. One is on longer T-on, one is on shorter T-on. So for very longer pulse on time, that is T-on, the more heat generation will be created between the tool and the interference contact between the workpiece and the tool. Next, it means it have a very high material removal rate and deeper craters and the very rough finishes. So shorter T-on, it has a very less heat generation between the tool and the workpiece and very smooth surface finish. In terms of material removal rate will be take place in a very significant lesser manner. So next is pulse off time. So pulse off time is the time between the two consecutive sparks. That is, purpose allows the molten material to solidify and depresses the flushes is being flushed away. Effect is the T off and T on, right? The spark gap is the distance between the electrode and the workpiece, where the effects will be obtaining in two phenomenon factor. One is on large gap, one is on smaller gap. So large gap will produces a better flushing with a very lower accuracy. The small gap will create a very high accuracy and precision with a very minimal amount of short circuiting during the operations factors. Next is selection of dielectric medium. There are various factors of choosing the dielectric mediums like kerosene, deionized water. Phenomenally, the most frequently in many industries, they will be using only the deionized water in electrical discharge machining process and also in EDM. So functions like it act as an insulators which break down flushing debris between the flushing pressures and the oxidation views. The cooling tool and the workpieces, it acts as a cooling chamber between the tool and the workpiece in order to reduce the deformation of the workpiece. So what is effect? So effect is the proper flushing. So proper flushing means it should have a proper stability machining factor, that is we called as machinability indexing factors. Next is poor dielectric medium, that is arching the pore surfaces and flushing pressure. The last one is effects. So normally we creates the effects on high pressure. So high pressure means the higher flushing debris from the workpiece may have a very reduces the tool wear, and lower pressure means unstable spark will generate it and we will have an irregular finish like scatter marks or debris on the workpieces. So now I am just going to tell you how the electrode material, that is common material like copper, graphite and brass. Normally electrode is being coated or uncoated. We can use the selection depends upon the following factors like polarities. So polarities is normally the tool can be of either positive or negative polarity. Either the positive polarity has some factors, negative polarity has some factors. So first is negative polarity has a very less number of tool wear and higher MRR, material removal rate. Whenever the tool is connected with the negative polarity, the material removal rate will be significantly higher when compared with the other factors. Next is positive factor. The positive polarity will have a very good surface finish with a very less number of tool wear. The next factor is in this factors, I'm just going to discuss about the latest literature survey how the traditional machining process versus unconventional machining process is being operated in the latest researches and by using of this techniques. So now the first paper is the minimization of residual stresses by using the electro-machining discharge of Inconel 625. So in this paper, they will be discussing on how the quality of the machined surface and reduces the tool wear and residual stress by using the Inconel 625 by using the optimal machining parameters like pulse on, pulse off, T current, IP current. By controlling them, we can easily obtain. So the EDM parameter is minimized by using 24.5% to 25.4% respectively. The second paper is modelizing the material behavior by using a special filament called the filament fabrication technique, where we are going to use a special techniques proposed consisting of the mathematical derivations by using of FE models, where we can easily understand and stimulate the behavior properties and virtual environmental by obtaining a physical and mechanical changes on the properties when it is compared with the microstructures. So next is the study of the stainless steel fabricated with filament fabrication techniques, where we can easily use a very high mechanical strength, and it is been comparatively machined with the help of argon temperature with a very high density like 7.1 grams per centimeter cube, whereas in the deformation rate is very less. So in this paper, the filament fabrication technique and scanning inversing the deformations, we are getting the novel approaches between to address the shrinkage and deformations, where we can get the exact positioning of the material with no oxidation or impurities inside the samples. So next is we are going to have a superalloys. The superalloys like novel SN625s. So in this we can easily know the IP current, voltage, duty factor, flushing pressure studies where the material removal rate and specific material removal rate can be easily analyzed by using a special technique called the field emission scanning electron microscope, where you can see the atomization distribution on the material removal rate when it is machined. Next one is EDM process by using the copper electrode by using Inconel 625. So this Inconel 625, where we are going to use a powdered nanoparticles. The powdered nanoparticle will be mixed in the dielectric medium, where the dielectric medium and this nanoparticle will mix together, and it will be mixed up at a certain pressure, and it will be led to the flowing nozzle. So the nozzle will get the flushing pressure of nano fluid, and as well as the dielectric medium, which will be focusing on the workpiece. In turns, the copper electrodes can improve a very high efficiency with a better surface finish with the nanoparticle which has been concentrated on the workpiece. Next is additive manufacturing on titanium alloys by using a special technique, a metal injection molding process. In this technique, we can usually use the mechanical properties like the metal fused filament fabrication technique, where the 17% and 1.7% of higher UTS and 17.5 higher elongations can be rejected, can be founded on this molded parts. Next is the feasibility on the metal fused filament fabrication technique. In this material, where we are going to use the stainless steel which can execute a metal extrusion technique which has a better and conventional methods for better alloying during the machining process. So next is the powder mixed with the titanium procedures, where we are going to use a special called ABS, that is acrylamide brodomide styrene is being coated with the layer. The thin layer of coated is being coated on the electrode as a powdered, and that powdered electrode is being used during the machining process, where you can easily identify the material removal rate, the tool wear, and the surface roughness has been measured, where it is seasonably higher and more significant. So in this paper, electrical discharge by using additive manufacturing, where the tool electrode having micro holes, machining fluid which flushes the debris out the element, and this significantly compared and accurately conventional copper tool during the machining process. So now I will be discussing on how the methodology can be easily deliberately shown in this flowchart. First is we are going to compare the conventional tool, additive tool, and what are the processing and pre-processing during the processing or during the AM additive manufacturing tool. So second process is selection of dielectric medium. The selection of dielectric medium can be of different stages like kerosene, mineral oil, deionized water. Why? In special cases we are going to use the EDM lubrication oils. Next is identify the special input parameters over the output parameters like material removal rate, surface roughness, overcut, and optimization technique, and we are going to have a fine result and discussions. So now I will be telling you what is the additive manufacturing copper tool over the triple F, that is metal fused filament fabrication technique. So in this diagram, the thin filament copper filament of diameter 1.75 mm diameter is being used as a copper filament. It is being fed into the filament transparent spool system, and it is fed to the nozzle. So this nozzle will be having the heating chamber. It will melt and evaporates the cooling chamber, and it will print the layer in XYZ direction, layer by layer. So next is the metal fused filament fabrication technique. It is operated on the principle how the EDM, that is FDM, that is fused deposition modeling, extruded through the heat nozzle, and it is layered and it is deposited by layer to create it in three directional axis, that is XYZ. So instead of the filaments, plastic filaments, you can use metal filaments in this procedure. So here are the parameters how we are going to use the filament fabrication techniques. The most important filament fabrication is, that is the filament, metal filament, nozzle temperature, built-up plate temperature, layer height, printing speed, and cooling. So filament, normal metal filament is this type. The composition of filament influences the properties of the printed parts. Next is nozzle temperature is the most important phenomenon factor that affects the viscosity and the flow of filament from the nozzle during the deposition rate. Next is build plate temperature. The temperature of the built plate ensures the additions between the first layer and the minimizing the wrapping process. Next is the layer height. So layer height is the thickness is where it deposited from XYZ directions and that determines the resolution on the surface finish of the part. Next is the printing speed and the cooling. So printing speed depends upon the time and the part quality, and the cooling is the cooling part between the layer and overheating that improves the stability of the workpiece. So next is how we are going to prepare the workpiece. So preparation is normally we design the tool, cross sectional of the tool, whether the tool is a cylinder or hexagonal or any other cross sectional in any software, that is SolidWorks or CATIA. Basic preparing on the 3D modeling, we are going to analyze in CAD system, that is computer aided machine drawing softwares. We can, after designing it, we have to slice it. The model is being sliced into very thin layers, generating the tool path which is being given as an input to the printers. Next is printing technologies, where the filament is being fed to the heating nozzles, where it is melted and extruded to the build plate layer by layer according to the programmable path which has been fed to the computer system. So in this, after the tool is being printed, we are going to directly have the washing zone. So washing zone is, the washing is a very best simplest technology where the metal 3D printers is being dissolved in the solvents. So normally we use the octane 695 solvent to wash it, where the binder material and the entire parts are penetrating deeper into the parts as it removes the polymer impurities. So the post processing, where all the printing part undergoes the additional process like the heat treatment, machining process, surface finish, in order to have a desirable, very good mechanical and physical properties, and also a surface quality during the machining process. So next slide I am just going to describe is what is the most important factor. So the left side I'm just going to tell you how the conventional machining tool is being fabricated. In this additive manufacturing tool is fabricated by layer. So the most effective additive manufacturing is the microstructure. Machinability on 625 will be carried out in the entire methodologies, and in the you will be knowing what is the comparative study between these two factors. The next one is, so the many researchers, we cannot blindly conclude that this is additive manufacturing is the most phenomenal factor. So for that we are going to have a set of experimentation values where we are going to compare them with the conventional versus the non-conventional process, that is additive special cases like metal fused filament fabrication, copper filaments. So now I am just going to have an experimentation table where first one is tool, that is 1 to 9 is the first tool, and second is 10 to 18 is second tool. So first 1 to 9 is I am just comparing it with the conventional tool. Next 10 to 18 is AM tool, that is additively manufacturing tool, with the three important input parameters like IP current, pulse current and pulse off, and I'm recording all the machining timing with respect to material removal rate, surface roughness and the overhead. So in this I'm just in the previous slide, after machining process, the entire sequence process will be clearly recorded with a special design of experiment optimization technique by using these techniques. So first is optimization of material removal rate. The optimization of material removal rate is the tool condition where the pulse current, pulse on duration, pulse off duration on the EDM control variable that affects the MRR. So in this table we can significantly note that the leading peak factor that affects the pulse current, that is pulse current and pulse on current of tool material and pulse off duration. So in the next slide I will be explaining you how the MRR will be shown in the graph. So with the best possible EDM control variables, it indicates that the highest material removal rate with the possible SNR ratio can frequently affecting the MRR with 15 amps on pulse current and 40 on pulse duration and 9 microseconds on pulse off duration, with which it clearly shows that with additively produced copper has a very tool fine material. So next is I'm just going to compare it with the ANOVA, where the significant factor on EDM is determined using the ANOVA, and the results can easily disclose in the above table, where the pulse current, the pulse on duration and the tool material, the control variables can be determined with the best impact on MRR, that is contributing factors. So these factors that is the pulse current, pulse duration and tool material. It gives us the various contribution on MRR, that is the pulse current on 82.72% of contribution, pulse on duration that is 10.48 contribution, tool material is 2.53% of contribution, a pulse off duration is 1.510. It indicates that the high level of significance factors on MRR on the following ratios. So next is influencing of control variables on MRR. So in the graph it clearly shows that the comparative study, the different tools materials, that is pulse current, it shows that different tool material means MRR with respect to high B current. So additive manufacturing copper tool produces the higher MRR than the traditional machining process. So next is optimization of surface roughness. The previous factor we have optimized the MRR and we have a set of values in which best parameters the highest MRR has been obtained. Whereas the second optimization, I am just going to move on with the surface roughness. Surface roughness is the main thing is the leading peak factor, that is pulse current, pulse T on tool material and pulse off duration will be considered. So next is among this graph, so most important thing is the most important significant factor, that is high surface roughness, where 5 amps of pulse current and 10% of pulse on duration and 5% of pulse off duration has been significantly produced with additive manufacturing as tool workpiece material. Next is I am just using the same technique in the previous MRR by using ANOVA. So in this factor, the most important factor is good enough to give the optimum and the significant comparative surface roughness and finding the best behavior on MRR by using the pulse on duration with the best contribution factors like pulse on duration is 50.83, pulse current is 13.5%, tool material is 5.99%, where the pulse off duration is 6.01, where it indicates that the high level of significant factors on the surface roughness shows the graphs. So next is I will be using the influence on the control variables on surface roughness, where the graph easily reveals that you can easily show that the black one is the traditional copper tool and the red one is AM copper tool. So AM traditional tool produces the maximum number of lower surface roughness than the traditional copper tool when it is compared with the other factors. So next is optimization of overcut. So internal diameter, difference between the internal overcut and the external overcut, we can easily differentiate the leading factors that affects the overcut like pulse on duration, pulse current material and pulse off duration. So next important factor is the analyzing on SN, that is signal to noise ratio. The overcut can be revealed on various significant factors like this indicates the highest possible SNR, that is the most important setting factors like the highest surface roughness like 5 amps and 10 micro durations and 10 pulse duration with highly produces the copper as the work tool material. So the next is by comparing it with the ANOVA table, the significant level of EDM control parameters was determined by using the ANOVA by using the various factors like the pulse current and pulse on duration was determined and the control variable to have the various percentage of contributions like the pulse on current with 83.45%, pulse current is 10.68% and tool material is 1.5% and pulse off duration is 0.29%, which has the very highest level of significant factors during the machining cutting process. So next is influencing the control variable on overcut. So the graph shows the traditional copper tool and unconventional copper tool. From this graph it is clearly revealed that the pulse on duration during the machining process increases the overcut on increment 6 to 5. So from this factor we can strongly state that additive manufacturing copper tool produces lower surface, produces a very lower overcut than the traditional copper tool. So here I am just going to deliberately explaining you about how the various factors with by comparing with the pie graph. So first is control variable on influencing MRR, where I am just going to use where the pulse current play a phenomenal vital role of 82.72% and second is pulse on duration, that is 10.48, the tool current material is 2.5% and pulse off duration is 2.53%, whereas the surface roughness, so the most important factor is the pulse on duration and the following factors like pulse current and the tool material, and followed by the pulse off current. The last one is the control variable influencing the overcut, where it is influencing on the pulse on current, followed by pulse current, tool material and the pulse off material. So this is the overall contributing factors by taking the control input parameters over the three important output parameters like MRR, surface roughness and overcut. So among this important factor, I have after machining the process, we are going to identify the SEM analyzing factor, how it is being machined. So in these two images, I have been kept the two SEM images. One is the surface of the Inconel 625 machined on additively AM tool, the surface machined on Inconel 625 by conventional tool. So here you can see the cluster formation and blisters are very less when compared to the conventional machining process. So it does not have any blow blisters or any cluster formations in AM, whereas you can find the many irregularities or irregular scratter mark in the conventional machining process. I can easily conclude my SEM analysis with the following inferences points in the following slides. So next is, I will be telling you the inferences slides, where I am just going to conclude my SEM images experimentation value with the following set of parameters. The first important set is the machined surface by AM, that is additively manufacturing tool, exhibits a very smooth and more uniform texture with a very lesser defects when avoiding the voids and indicating superior super finish when compared to conventional tool. The second point is the AM tool, as shown in the SEM diagram, has a very better controlled over the workpiece material, resulting in the lower cut by evidencing the minimal edges, erosion and more precise boundaries in the SEM images. The third one is the surface. Talking about the surface, we are going to talk about how the finer structures with the uniform crater marks, distributions and few very less number of recast layer, where very less number of recast layer is shown in the SEM images and more on the unconventional machining process. But both surfaces and the conventional tool where with the irregularities and larger crater mark and uneven recrest indicating the poor surface finish can be easily obtained. The additive manufacturing tool, that is smoother and non-smoother finishes between the supercut and making it in a more effective presents manner and on the Inconel 625. So I could like to conclude with the references which has been done on the following process. So taking the tool, there is a special tool called additively manufacturing copper tool by using a filament fabrication technique over the conventional tool, that is normal conventional tool. The following set of parameters after machining on the EDM X25 shows the phenomenon factor that and conclude that additive manufacturing copper tool is more phenomenon factor than the conventional tool. In the upcoming research and upcoming sessions, the additively manufacturing tool will be taken forward for the specially treated process like cryogenic. So this cryogenic tool will be dipped in the liquid nitrogen for 12 hours, 36 hours and 48 hours. After that, in the same phenomenon factor, we can do many case studies knowing that the newly apparently developed tool on the EDM shows the phenomenon factor in the unconventional machining process. So hope the session was very useful for all the students. So in upcoming my sessions, I will be explaining you how the additive manufacturing tool is being carried forward on the cryogenically treated tool with some useful applications oriented. So thank you very much. So once again, thank you. I am Murali, an assistant professor, Department of Mechanical Engineering, giving me this golden opportunity to convey this useful session for my students. So see you on another video. Thank you all.